Hello everyone, welcome to our next lecture in our physiology video lecture series. This particular lecture is titled Aviation, Space and Deep Sea Diving Physiology. In this particular lecture, we will go through specific conditions that the human body can be put to, namely during aviation or flight, or space travel, or deep sea diving, and how our body copes with all these specific scenarios. So let us go into the slides. First, we will look into high altitude physiology. At higher altitude, the atmospheric pressure starts dropping. The reason behind this is that the force of gravity decreases as one ascends. This causes air molecules to be less packed at higher altitudes, and this in turn causes low barometric pressures. So as the force of gravity is acting less and is less powerful as we ascend higher and higher, the effect of gravity on air molecules that pack it together to essentially form the barometric pressure is low. Thus, air molecules at higher altitudes are less packed together and thus produce a low barometric pressure. The table below here shows approximate barometric and oxygen pressures at different altitudes. So barometric pressure is essentially the atmospheric pressure due to all the gases present in the atmosphere, and oxygen pressure is specific to only the pressure exerted by oxygen. And this particular table shows the different pressures at sea level, which is shown as 0 feet altitude, and gradually it rises. And we can see that the barometric pressure is 760 millimeters of mercury at the sea level of 0 feet of altitude. At 10,000 feet, the barometric pressure drops down to 523 millimeters of mercury. And at 50,000 feet, it is just 87 millimeters of mercury. This decrease in barometric pressure is the basic cause of all the hypoxia problems in high altitude physiology. Hypoxia means low oxygen level problems. Because as barometric pressure decreases, the atmospheric oxygen partial pressure decreases proportionately, remaining at all times slightly less than 21% of total barometric pressure. And thus this means that PO2 at sea level is around 159 millimeters of mercury, but at 50,000 feet it only becomes 18 millimeters of mercury. Thus what we get from this slide is that since partial pressure of oxygen is a percentage of the total barometric pressure, as the total barometric pressure drops as we ascend in altitude, the partial pressure of oxygen also drops, and it can reduce to a quite low value of 18 millimeters of mercury as we rise up to heights of 50,000 feet. This low partial pressure of oxygen is what causes the hypoxia or low oxygen level conditions, which affect the high altitude physiology. So what exactly is the effect of the low oxygen or the hypoxic condition is what we will look into in this slide. Thus, we will look into the effects of low oxygen pressure and alveolar PO2s or partial pressure of oxygen at high altitudes. The carbon dioxide and water vapor present in the air decrease the alveolar oxygen. Even at high altitudes, carbon dioxide is continually excreted from the pulmonary blood into the alveoli. Also, water vaporizes into the inspired air from respiratory surfaces. These two gases dilute oxygen in the alveoli, thus reducing the oxygen concentration. Water vapor pressure in the alveoli remains 47 millimeters of mercury as long as the body temperature is normal, regardless of the altitude. At the top of Mount Everest, which is around 29,028 feet, the barometric pressure falls from normal sea level value of 760 millimeters of mercury to only 253 millimeters of mercury. Out of this 253 millimeters of mercury, 47 millimeters of mercury must be water vapor, as we just discussed. This leaves only 206 millimeters of mercury for all other gases. In an acclimatized person, that is a person who can breathe at a high altitude, 7 millimeters of 7 millimeters of this 200 millimeters of mercury pressure that is left must be carbon dioxide, thus leaving only 199 millimeters of mercury. If there were no use of oxygen by the body, 1/5 of this 199 millimeters of mercury would be oxygen and 4/5 will be nitrogen. That is, the PO2 in alveoli would be around 40 millimeters of mercury. However, some of this remaining alveolar oxygen is continually being absorbed into the blood, and this leaves only 35 millimeters of mercury oxygen pressure in the alveoli. Thus, at the summit of Mount Everest, only the best of acclimatized person can barely survive while breathing normal air, because only 35 millimeters of mercury of partial pressure of oxygen is allowed or is present there. But the effect is very different when a person is breathing pure oxygen, because in this case, no question of nitrogen or carbon dioxide comes into the picture. Or rather, no question of nitrogen comes into the picture, as we will see in later slides. So we will also look at saturation of hemoglobin with oxygen at higher altitudes. The figure that is shown here shows arterial blood oxygen saturation at different altitudes while a person is breathing air and while the person is breathing pure oxygen. Up to an altitude of 10,000 feet, even when air is breathed, the arterial oxygen saturation remains at least as high as 90%. This is mainly because of the efficient hemoglobin oxygen buffer system that we have already discussed in previous videos. Above 10,000 feet, the arterial oxygen saturation falls rapidly, as shown by the blue curve in the figure. We can see a sharp drop in the oxygen saturation until it is slightly less than 70% at 20,000 feet and much less at still higher altitudes. So this was the case when a person is breathing air at higher altitudes. The arterial oxygen saturation drops sharply after one ascends above 20,000 feet. But what is the effect when a person is breathing pure oxygen? The red curve shows the arterial blood hemoglobin oxygen saturation at different altitudes when one is breathing pure oxygen. Note that the saturation remains above 90% until the aviator ascends to about 39 per thousand feet. Aviator is a person who is flying a jet or a plane, because obviously at 39,000 feet, that is the only way we can reach that particular altitude. Then it falls rapidly to about 50% at about 47,000 feet. So we are now looking at the red line, in which we can see that around 39,000, 40,000 feet, the oxygen saturation still remains close to 90%, whereas this limit was reached while breathing normal air at about 10,000 feet. And as we ascend even further, this oxygen saturation drops to 50% at around 47,000 feet. When a person breathes pure oxygen instead of air, most of the space in the alveoli formerly occupied by nitrogen becomes occupied by oxygen. At 30,000 feet, an aviator could have an alveolar PO2 as high as 139 millimeters of mercury instead of just 18 millimeters of mercury when breathing air. And thus, when a person is breathing pure air, oxygen at higher altitudes, the chances of his survival are way better. And thus, we know that mountain climbers always carry oxygen cylinders with them and do not depend on the air that is present on mountains. That is, they do not breathe normal air. And this is the reason why they do this. Next, we'll look into the ceiling when breathing air and when breathing oxygen in an unpressurized air. Comparing the two arterial blood oxygen saturation curve that we just saw, one notes that an aviator breathing pure oxygen in an unpressurized airplane can ascend to far higher altitudes than one breathing air. For instance, the arterial saturation at 47,000 feet when one is breathing oxygen is about 50% and is equivalent to the arterial oxygen saturation at 23,000 feet when one is breathing air. In addition, because an unacclimatized person usually can remain conscious until the arterial oxygen saturation falls to about 50%, for short exposure times, the ceiling for an aviator in an unpressurized airplane when breathing air is about 23,000 feet, and when breathing pure oxygen is about 47,000 feet, provided that the oxygen supplying equipment obviously works perfectly. And this is why we see that in most cases, aviators flying jet airplanes, which go to even higher altitudes, always have air masks on so that they can continue breathing pure oxygen, so that their ceiling or the maximum height or altitude they can reach while flying the plane increases or is high enough that they can easily survive that altitude. The fifth column that is shown here, that this is the table that we have already seen in the first slide, shows that approximately PO2s in the alveoli at different altitudes when one is breathing air for both the unacclimatized person and the acclimatized person. So we are talking about this particular column right here, which shows, or rather this particular column, which shows in the normal writing the PO2 in alveoli present for an unacclimatized person, and within parentheses the PO2s for an acclimatized person. At sea level, the alveolar PO2 is 104 millimeters of mercury for both the acclimatized and unacclimatized person. At 20,000 feet of altitude, it falls to about 40 millimeters of mercury in the unacclimatized person, but only to 53 millimeters of mercury in the acclimatized person. The difference between these two is that alveolar ventilation increases much more in the acclimatized person than in the unacclimatized person. And as we have already discussed in the last lecture, that in an acclimatized person, the regulation of breathing is no longer dependent on the concentration of carbon dioxide present in their blood, and that is why the alveolar ventilation rate can increase much more, and this is the determining factor which results in higher PO2s for the acclimatized person. If we are having difficulty in recalling this information, we can always go back and refer to the previous lecture in which we have discussed this particular regulation in detail. Next, we'll look into the acute effects of hypoxia or low oxygen level concentrations. Some of the important acute effects of hypoxia in an unacclimatized person breathing air, which begin at around 12,000 feet, are drowsiness, lassitude, that is a feeling of laziness, mental and muscle fatigue, headache, occasionally nausea, and sometimes euphoria or the feeling of happiness. These effects progress to a stage of twitchings or seizures above 18,000 feet and end above 23,000 feet in the unacclimatized person in coma, followed shortly thereafter by death. Thus, these symptoms continue to around 18,000 feet, after which the symptoms of hypoxia become even more severe, and at around 23,000 feet, an unacclimatized person can fall into coma, followed shortly after death. One of the most important effects of hypoxia is decreased mental proficiency, which decreases judgment, memory, and performance of discrete motor functions. For instance, if an unacclimatized aviator stays at 15,000 feet for 1 hour, mental proficiency ordinarily falls to about 50% of normal. And after 18 hours at this level, it falls to about 20% of normal. Next, we look into acclimatization to low PO2s. A person remaining at high altitudes for days, weeks, or years becomes more and more acclimatized to the low PO2 so that it causes fewer deleterious effects on the body. And it becomes possible for the person to work harder without hypoxic effects or to ascend to even higher altitudes. The principal means by which acclimatization comes about are a great increase in pulmonary ventilation, increased number of red blood cells, increased diffusing capacity of the lungs, increased vascularity of the peripheral tissues, and increased ability of the tissue cells to use oxygen despite low partial pressure of oxygen. First, we look into the first one of them, which is increased pulmonary ventilation, which is essentially the role of arterial chemoreceptors. Immediate exposure to low PO2s stimulates the arterial chemoreceptors, and this increases alveolar ventilation to a maximum of about 1.65 times normal. Then, if a person remains at a very high altitude for several days, the chemoreceptors increase ventilation still more, up to about 5 times normal. The immediate increase in pulmonary ventilation on rising to a high altitude blows off a large quantity of carbon dioxide, which in turn reduces the partial pressure of carbon dioxide and increases the pH of body fluids. These changes inhibit the brainstem respiratory center and thereby oppose the effect of low PO2 to stimulate respiration by way of peripheral arterial chemoreceptors in the carotid and the aortic bodies. Thus, this excess blow-off of carbon dioxide prevents increasing pulmonary ventilation. But during the ensuing 2 to 5 days, as the person remains at a high altitude, this inhibition fades away, following the respiratory center to respond with full force to the peripheral chemoreceptor stimulus from hypoxia, and ventilation increases to about 5 times normal. Thus, in the initial days, the regulatory center in our brain for respiration is dependent majorly on carbon dioxide levels. And as more and more carbon dioxide gets blown off as pulmonary ventilation increases, the rate of pulmonary ventilation is thus controlled so that the amount of carbon dioxide that is blown off is not a huge or not a lot. But after 2 to 5 days that a person remains at a high altitude, this particular blow off of carbon dioxide is now not the major source of control for pulmonary ventilation, as this particular inhibition fades. And the body then moves towards low oxygen or hypoxia condition as the major marker for how much pulmonary ventilation is required. And after 2 to 5 days, the pulmonary ventilation increases little by little to about 5 times normal in order to maintain normal oxygen conditions even at higher altitudes. Next is increase in red blood cells and hemoglobin concentration during acclimatization. Hypoxia is the principal stimulus for causing an increase in red blood cell production. Ordinarily, when a person remains exposed to low oxygen for weeks at a time, the hematocrit rises slowly from a normal value of 40 or 45 to an average of about 60. With an average increase in whole blood hemoglobin concentration from normal of 15 grams per deciliter to about 20 grams per deciliter. In addition, the blood volume also increases, often by 20 to 30%. And this increase times the increased blood hemoglobin concentration gives an increase in total body hemoglobin of 50% or more. Thus, there is an overall increase in red blood cell and hemoglobin concentration during acclimatization as well. Next is the increased diffusing capacity after acclimatization. The normal diffusing capacity for oxygen through the pulmonary membrane is about 21 milliliters per millimeter of mercury per minute. And this diffusing capacity can increase as much as threefold during exercise. A similar increase in diffusing capacity occurs at high altitude. Part of the increase results from increased pulmonary capillary blood volume, which expands the capillaries and increases the surface area through which oxygen can diffuse into the blood. Another part results from increase in lung air volume, which expands the surface area of alveolar capillary interface still more. A final part results from an increase in pulmonary arterial blood pressure. This forces blood into greater number of alveolar capillaries than normally, especially in the upper parts of the lungs, which are poorly perfused under usual conditions. Next, we look into the peripheral circulatory system changes during acclimatization, which is mainly increased tissue capillarity. Another circulatory adaptation is growth of increased number of systemic circulatory capillaries in the non-pulmonary tissues, which is called increased tissue capillarity or angiogenesis. That is the formation of new blood vessels. This occurs especially in animals born and bred at high altitudes, but less so in animals that later in life become exposed to high altitudes. In active tissues exposed to chronic hypoxia, the increase in capillarity is especially marked. For instance, capillary density in right ventricular muscle increases markedly because of the combined effects of hypoxia and excess workload on right ventricle caused by pulmonary hypertension at high altitudes. Next, we look into cellular acclimatization. In animals native to altitudes of 13,000 to 17,000 feet, cell mitochondria and cellular oxidative enzyme systems are slightly more plentiful than in sea level inhabitants. Therefore, it is presumed that tissue cells of high altitude acclimatized human beings also can use oxygen more effectively than can their sea level counterparts. Next, we look at natural acclimatization of native human beings living at high altitudes. In the last 2 points of acclimatization, we have looked into that animals or humans that are born at high altitudes and have lived most of their lives at that level are much better acclimatized to the high altitude conditions due to cellular acclimatization and increased tissue capillarity. This stark difference between sea level human beings and living at high altitudes is demonstrated in this particular graph. Many native human beings in Andes and in the Himalayas live at altitudes above 13,000 feet. One group in the Peruvian Andes lives at an altitude of 17,500 feet and works a mine at an altitude of 19,000 feet. Many of these natives are born at these altitudes and live all their lives at that level. In all aspects of acclimatization, the natives are superior to even the best acclimatized lowlanders, even though the lowlanders might also have lived at high altitudes for 10 or more years. Acclimatization of natives begins in infancy. The chest size especially is greatly increased, whereas the body size is somewhat decreased, giving a high ratio of ventilatory capacity to body mass. In addition, their hearts, which from birth onward pump extra amounts of cardiac output, are considerably larger than hearts of lowlanders. Delivery of oxygen by the blood to the tissues is also highly facilitated in these natives. For instance, the figure above, which is right here, shows the oxygen hemoglobin dissociation curves for natives who live at sea level and for the counterparts who live at 15,000 feet. That is the blue line for the sea level dwellers, and mountain level dwellers are the red. Note that the arterial oxygen PO2s in the natives at high altitude is only 40 millimeters of mercury, but because of the greater quantity of hemoglobin, the quantity of oxygen in their arterial blood is greater than in the blood of natives at lower altitudes. So what we mean by that is that at 40 millimeters of partial pressure of oxygen, if we draw a line right here, we can see the quantity of oxygen in the blood for mountain dwellers is close to 21%, whereas it is close to 16% for sea level dwellers. Thus, at a low partial pressure of oxygen of only 40 millimeters of mercury, the mountain dwellers are able to utilize the oxygen much better due to their acclimatized bodies or their acclimatized physiology. Note also that the venous PO2s in the high altitude natives is only 15 millimeters of mercury less than the venous PO2s in lowlanders, despite the very low arterial PO2s, indicating that the oxygen transport to the tissues is exceedingly effective in naturally acclimatized high altitude natives. So if we compare, if we draw a horizontal line joining these two values essentially, we are able to see that even though that the quantity of oxygen in the venous blood for both the mountain dwellers and the sea level dwellers are more or less the same, even though the mountain dwellers are subjected to much lower arterial values of PO. This means that the mountain dwellers are able to absorb much higher amount of oxygen from the blood, even at low concentrations of atmospheric oxygen, than the sea level dwellers. Next, we change gears and move on to accelerative effects of acceleratory forces on body in aviation and space physiology. So we will now talk about action of different acceleratory forces that act on our body, and we have now covered the acclimatization and effects of oxygen part of high altitude physiology. Because of rapid changes in velocity, direction of motion in airplanes or spacecraft, Several types of acceleratory forces affect the body during flight. At the beginning of flight, simple linear acceleration occurs. At the end of flight, deceleration, and at every turn of the vehicle, centrifugal acceleration is acted upon the body. So first let us look into centrifugal acceleratory forces. When an airplane makes a turn, the force of centrifugal acceleration is determined by the following relation, which is F equal to mv square by r, in which F is centrifugal acceleratory force, m is the mass of the object, v is velocity of travel, and r is the radius of curvature of the turn. From this formula, it is obvious that as velocity increases, the force of centrifugal acceleration increases proportionately to the square of velocity. It is also obvious that as force of acceleration is directly proportional to the sharpness of the turn or inversely proportional to the radius. So we ordinarily measure acceleratory forces in terms of G. That is, when an aviator is simply sitting in his seat, the force with which he is pressing against the seat results from the pull of gravity and is equal to his weight. The intensity of this force is said to be plus 1g because it is equal to the pull of gravity. If the force with which he presses against the seat becomes 5 times his normal weight during pull out from a dive, the force acting on his seat is plus 5g. If an aeroplane goes through an outside loop so that the person is held down by his seatbelt, negative g is applied to his body. If the force with which he is held down by the weight is equal to the weight of his body, the negative force that is applied on his body is obviously minus 1g. We first then look into the effects of centrifugal acceleration on the body, that is positive g. The effect, first we look into the effects on vertebrae. Extremely high acceleratory forces, for even a fraction of a second, can fracture the vertebrae. The degree of positive acceleration that the average person can withstand in the sitting position before vertebral fracture occurs is about 20 G. Next, we look into effect on circulatory system. The most important effect of centrifugal acceleration is on the circulatory system, because blood is mobile and can be translocated by the centrifugal forces. When an aviator is subjected to positive G, blood is centrifuged towards the lowermost part of the body. Thus, if the centrifugal acceleratory forces is plus 5G and the person is immobilized in a standing position, the pressure in the veins of the feet become greatly increased to about 450 millimeters of mercury. In the sitting position, the pressure becomes nearly 300 millimeters of mercury. And as pressure in the vessels of the lower body increases, these vessels passively dilate so that a major portion of the blood from the upper body is translocated into the lower vessels. Because the heart cannot pump unless blood returns to it, the greater quantity of blood pooled in this way to the lower body, the less that is available for the cardiac output. Thus, the whole effect of this acceleratory forces is that blood gets pooled in the lower parts of our body, and the cardiac output decreases, and thus this can be very dangerous for an aviator that is flying at high G's. The figure here shows the change in systolic and diastolic arterial pressures, where the systolic curve is the one above and the diastolic curve is the one below. In the upper body, when a centrifugal acceleratory force of plus 3.3 G is suddenly applied to a sitting person, note that both these pressures fall below 22 millimeters of mercury for the first few seconds after the acceleration begins, but then return to a systolic pressure of about 55 millimeters of mercury and a diastolic pressure of 20 millimeters of mercury within another 10 to 15 seconds. This secondary recovery is caused mainly by activation of baroreceptor reflexes. Acceleration greater than 4 to 6 G causes blackout of vision within a few seconds and unconsciousness shortly thereafter. If this great degree of acceleration is continued, the person will die, which is obvious as blood is no longer being pumped throughout the body, and this can be fatal for the aviator who is traveling at high G's such as 4 to 6 G. Now, after looking at the effects of positive G, we'll look at the effects of negative G. The effects of negative G are on the body are far less dramatic acutely, but possibly more damaging, permanently than the effects of positive G. An aviator can usually go through outside loops up to negative acceleratory forces of -4 to -5 G without causing permanent harm, although causes intense momentary hyperemia of the head. Occasionally, psychotic disturbances lasting for 15 to 20 minutes occur as a result of brain edema. Occasionally, negative G forces can be so great, -20 G for instance, and centrifugation of blood into the head is so great that the cerebral blood pressures reach up to 300 to 400 millimeters of mercury, sometimes causing small vessels on the surface of the head and in the brain to rupture. However, the vessels inside the cranium show less tendency for rupture than would be expected for the following reason. The cerebrospinal fluid is centrifuged towards the head at the same time that the blood is centrifuged towards the cranial vessels. And the greatly increased pressure of the cerebrospinal fluid acts as a cushioning buffer on the outside of the brain to prevent intracerebral vascular rupture. Because the eyes are not protected by the cranium, intense hyperemia occurs in them during strong negative G. As a result, the eyes often become temporarily blinded with redout, which is caused by rupture of blood vessels present in the eye, and thus the blood covers the entire eye and causes a redout in which the aviator cannot see his surroundings. And thus, as we have seen that the centrifugal accelerative forces can be very dangerous for the aviator, and thus certain protections need to be taken against them. And what are these protections is what we'll look into in this particular slide. Specific procedures and apparatus have been developed to protect aviators against circulatory collapse that might occur during positive G. First, if the aviator tightens his or her abdominal muscle to an extreme degree and leans forward to compress the abdomen, some of the pooling of the blood in the large vessels of the abdomen can be prevented, thereby delaying the onset of blackout. Also, special anti-G suits have been devised to prevent pooling of blood in the lower abdomen and legs. The simplest of these applies positive pressure to the legs and abdomen by inflating compression bags as the G increases. Theoretically, a pilot submerged in a tank or a suit of water might experience little effect of G forces on circulation because pressure developed in the water is pressing against the outside of the body during centrifugal acceleration would almost exactly balance out the forces acting in the inside of the body. However, the presence of air in the lungs still allows displacement of heart, lung tissues, and diaphragm into seriously abnormal position despite submersion in water. Therefore, even if this procedure were used, the limit of safety almost certainly would still be less than 10 G. Thus, essentially, even with various protection gears, an aviator should not be exposed to greater than 10 G for long periods of time. Next, we look into effects of linear acceleratory forces on the body. First, we look into acceleratory forces in space travel. Unlike an airplane or spacecraft cannot make rapid turns. Therefore, centrifugal acceleration is of little importance, except when the spacecraft goes into abnormal gyrations. However, blast off acceleration and landing deceleration can be tremendous. Both of these types are linear acceleration, one positive and one negative. Now, figure that we'll look into the next slide is an approximate profile of the acceleration during blast off in a three-stage spacecraft, demonstrating that the first stage booster causes acceleration as high as 9g, the second stage booster as high as 8g. In the standing position, the human body could not withstand this much acceleration, but in a semi-reclining position transverse to the axis of acceleration, this amount of acceleration can be withstood with ease, despite the fact the acceleratory forces continue for as long as several minutes at a time. Therefore, this is the reason we see astronauts seated in reclining seats, because this is very much effective to counteract the ill effects of linear acceleratory forces that their bodies are subjected to. So this is the particular figure that we're talking about. So we can see that during the first booster of the rocket, the acceleratory forces can reach up to 9g, which then falls off sharply as the second booster takes off, and the acceleratory forces reach up to 8g. The problem also occurs during deceleration when the spacecraft re-enters the atmosphere. A person traveling at Mach 1, that is the speed of sound and of fast airplanes, can be safely decelerated in a distance of about 0.12 miles. Whereas a person traveling at a speed of Mach 100, a speed which is possible in interplanetary space travel, would require a distance of about 10,000 miles for safe deceleration. The principal reason for this difference is that the total amount of energy that must be dispelled during deceleration is proportionate to square of the velocity, which alone increases the required distance for decelerations between Mach 1 versus Mach 100 to about 10,000 fold. But in addition to this, a human being can withstand far less deceleration if the period of deceleration acts for a long time than for a short time. Therefore, deceleration must be accomplished much more slowly from higher velocities than is necessary at lower velocities. Thus, essentially, decelerating to a stop in space travel is also very complicated and can be dangerous for the astronauts that are in the spacecraft, as the higher the velocity, the greater amount of distance that is required to stop the spacecraft to a complete rest, as well as this time period should be long enough so that the person's body or the astronaut's body does not face any ill effects due to the sudden deceleration. Next, we look into another aspect of space travel, which is the artificial climate which is created in a sealed spacecraft. Because there is no atmosphere in the outer space, an artificial atmosphere and climate must be produced in the spacecraft. Most importantly, the oxygen concentration must remain high enough and carbon dioxide concentration low enough to prevent suffocation. In some earlier space missions, a capsule atmosphere containing pure oxygen at about 260 millimeters of mercury pressure was used. But modern space shuttles, gases about equal to those in normal air are used, with 4 times as much nitrogen as oxygen and a total pressure of 760 millimeters of mercury. The presence of nitrogen in the mixture greatly diminishes the likelihood of fire and explosion. For space travel lasting more than several months, it is impractical to carry an adequate oxygen supply, which will obviously be finished by the time the astronauts are well into their way in space. For this reason, recycling techniques have been proposed for use of same oxygen over and over again. Some recycling processes depend on purely physical procedures such as electrolysis of water to release oxygen, whereas others depend on biological methods such as use of algae with their large store of chlorophyll to release oxygen from carbon dioxide by the process of photosynthesis. Next, let us talk about weightlessness in space. A person in an orbiting satellite or a non-propelled spacecraft experiences weightlessness or a state of near zero g-force, which is sometimes called microgravity. That is, the person is not drawn towards the bottom, sides, or top of the spacecraft, but simply floats inside its chambers. The cause of this is not failure of the gravity to pull on the body, but because gravity from any nearby heavenly body is still active. However, the gravity acts on both the spacecraft and this person at the same time, so that both are pulled with exactly the same acceleratory forces and in the same direction. For this reason, the person simply is not attracted towards any specific wall of the spacecraft. Similar situation can be observed in a free-falling lift with passengers inside. The passengers will also fall along with the lift at a rate of small g, which is 9.8 meter per second square, and thus they will also feel the state of near weightlessness, as they are not being attracted to any of the surfaces of the lift but can easily float around inside the lift itself. The scenario is similar for astronauts present in a sealed spacecraft. So let us move on to the physiologic problems of weightlessness or microgravity. So the weightlessness problem is what we just discussed, and the astronauts have to face weightlessness for extended periods of time. This can prove problematic at various levels, which we will look into at the moment. The physiologic problems of weightlessness have not proved to be of much significance, as long periods of weightlessness is still not too long. Most of the problems that do occur are related to three effects of weightlessness. The first is motion sickness during the first few days of travel. Second is translocation of fluid within the body because of the failure of gravity to cause normal hydrostatic pressures. Third is the diminished physical activity because no strength of muscle contraction is required to oppose the force of gravity. The observed effects of prolonged stay in space are as follows. This include decrease in blood level, decrease in red blood cell mass, decrease in muscle strength and work capacity, decrease in maximum cardiac output, and loss of calcium and phosphate from bones, as well as loss of bone mass. Most of these same effects also occur in people who lie in bed for extended period of time. For this reason, exercise programs are carried out by astronauts during prolonged space missions, so that the various physiological effects of weightlessness do not affect their physiology much. Next, we change gear and finally arrive at the physiology of deep sea diving and other hyperbaric conditions or high pressure conditions. When human beings descend beneath the sea, the pressure around them increases tremendously. To keep the lungs from collapsing, air must be supplied at a very high pressure to keep them inflated. This exposes the blood in the lungs also to extremely high alveolar gas pressure, a condition called hyperbaric. Beyond certain limits, these high pressures can cause tremendous alterations in body physiology and can be lethal. First, let us look into the relationship between pressure and sea depth. A column of seawater 33 feet deep exerts the same pressure at its bottom as the pressure of atmosphere above the sea. Therefore, a person 33 feet beneath the water or ocean surface is exposed to 2 atmospheres pressure, which can be seen from the table right here. So sea level is 1 atmospheric pressure and 33 feet of the sea, 33 feet below the sea level is 2 atmospheric pressure. Another important detail is the effect of depth is in compression of gases to smaller and smaller volumes. The lower part of the figure shows a bell jar at sea level containing 1 liter of air. At 33 feet beneath the sea, where the pressure is 2 atmospheres, the volume has compressed to only about 1/2 liter. And at 8 atmospheres, which is around 233 feet, to 1/8 of a liter. Thus, the volume to which a given quantity of gas is compressed is inversely proportional to the pressure. This is a principle of physics which is called Boyle's law, which is extremely important in diving physiology because increased pressure can collapse the air chambers of the diver's body, especially the lungs, and often cause serious damage. Thus, essentially, as a column of air travels further and further below the sea surface, it is compressed to very minute, compressed under the tremendous pressure to a fraction of the volume it once occupied at sea level. This is analogous to the air column that is air that is present in our lungs, and due to the tremendous pressure of water around us at the very high depths or very low depths, the air in our lungs can be compressed to a fraction of the volume they once occupied at sea level, and this can prove fatal and also have serious damage on our body. Now we'll look into the effects of partial pressures of individual gases on the body, which and we'll look specifically at the gases, at the breathing gases, which are nitrogen, oxygen, and carbon dioxide, and the significant physiologic effects that these 3 gases cause at high pressures. First, we will look into nitrogen narcosis at high nitrogen pressures. About 4/5 of the air is nitrogen. At sea level pressure, nitrogen has no significant effect on bodily function. But at high pressures, it can cause varying degrees of narcosis. When a diver remains beneath the sea for an hour or more and is breathing compressed air, the depth at which the first symptoms of mild narcosis appear is about 120 feet. At this level, the diver begins to exhibit joviality and to lose many of his or her capes. At about 150 to 200 feet, the diver becomes drowsy. At 200 and 250 feet, his or her strength wanes considerably, and the diver often becomes too clumsy to perform the work required. Beyond 250 feet, which is 8.5 atmospheric pressures or more, the diver usually becomes almost useless as a result of nitrogen narcosis if he or she remains at these depths for too long. Nitrogen narcosis has characteristics similar to those of alcohol intoxication. And for this reason, it has been frequently been called raptures of the death. The mechanism of narcotic effect is believed to be the same as that of most other gas anesthetics. That is, it dissolves in the fatty substances of neuronal membranes, and because of its physical effect on altering ionic conductances through the membranes, this reduces neuronal excitability and causes the narcotic effect. Next, we move into oxygen toxicity at high pressures. We first look into the effect of very high PO2 on blood oxygen transport. When PO2 in the blood rises above as we are saying, we look into the effect of very high PO2 on blood oxygen transport. When PO2 in the blood rises above 100 millimeters of mercury, the amount of oxygen dissolved in water of the blood increases markedly. This is shown in the figure right here, which depicts the oxygen hemoglobin dissociation curve with the alveolar PO2 extended to more than 3000 millimeters of mercury. Also depicted by the lowest curve in the figure is the volume of oxygen dissolved in the fluid of the blood at each PO2 level. Note that in the normal range of alveolar PO2, which is below 120 millimeters of mercury, almost none of the total oxygen in the blood is accounted for by the dissolved oxygen. But as the oxygen pressure rises to thousands millimeters of mercury, a large portion of total oxygen is then dissolved in the water of the blood, in addition to that bound with the hemoglobin. So we can see right here, the oxygen hemoglobin dissociation curve has a steep boundary or saturates right here, and the blue line shows total oxygen that is present in blood. And thus, if this is the saturation of the oxygen hemoglobin buffer system, this excess oxygen is obviously traveling by dissolving in the water of the blood due to high PO2 levels. And this is what this high oxygen in the blood water is what causes the oxygen poison. Next, we look into effect of high alveolar PO2 on tissue PO2. Let us assume that PO2 in the lungs is about 3000 millimeters of mercury, which is around 4 atmospheric pressure. Referring to the figure, one finds that this represents a total oxygen content in each 100 millimeters of blood of about 29 volumes per cent, as demonstrated by point A in the figure. This means 20 volumes per cent bound with hemoglobin and 9 volumes per cent dissolved in the blood water. As this blood passes through tissue capillaries, the tissues use their normal amount of oxygen, about 5 millimeters from each 100 milliliters of blood. The oxygen content on leaving the tissue capillaries is still 24 volumes per cent, which is shown as point B. At this point, PO2 is approximately 1200 millimeters of mercury, which means that oxygen is delivered to the tissues at this extremely high pressure instead of a normal value of 40 millimeters of mercury. Thus, once the alveolar PO2 rises above a critical level, the hemoglobin oxygen buffer mechanism is no longer capable of keeping the tissue PO2 in the normal safe range between 20 to 60 millimeters of mercury. Next, we look into acute oxygen poisoning and oxidizing free radicals. The extremely high tissue PO2 that occurs when oxygen is breathed at very high alveolar oxygen pressure can be detrimental to many of the body's tissues. For instance, breathing oxygen at 4 atmospheres pressure of oxygen, which is PO2 equal to 3040 millimeters of mercury will cause brain seizures followed by coma in most people within 30 to 60 minutes. Other symptoms encountered in acute oxygen poisoning include nausea, muscle twitchings, dizziness, disturbances of vision, irritability, and disorientation. Chronic oxygen poisoning can also cause pulmonary disability. A person can be exposed to only 1 atmosphere pressure of oxygen almost indefinitely without developing acute oxygen toxicity of the nervous system that we just described. However, after only about 12 hours of 1 atmosphere oxygen pressure exposure, lung passageway congestion, pulmonary edema, and atelectasis caused by damage to the linings of the bronchi and alveoli begin to develop. The reason for this effect in the lung, but not in other tissues, is that air spaces of lungs are directly exposed to the high oxygen pressure, but oxygen is delivered to the body at almost normal PO2 because of the hemoglobin oxygen buffer system. And thus, an increase in partial pressure of oxygen affects the lungs directly before affecting any other parts of the body. Next, we look into oxidizing free radicals. Excessive intracellular oxidation as a cause for nervous system oxygen toxicity. There are several forms of active oxygen called oxygen-free radicals. One of the most important of these are the superoxide free radical and the peroxide radical. Even when the tissue PO2 is normal at the level of 40 millimeters of mercury, small amounts of free radicals are continually being formed from the dissolved molecular oxygen. Fortunately, the tissues also contain multiple enzymes that rapidly remove these free radicals, which include peroxidases, catalases, and superoxide dismutases. Therefore, so long as the hemoglobin oxygen buffering mechanism maintains a normal tissue PO2, the oxidizing free radicals are removed rapidly enough that they have little or no effect in the tissues. Above a critical alveolar PO2, that is above 2 atmospheres of PO2, the hemoglobin oxygen buffering mechanism fails, and the tissue PO2 can then rise to hundreds or thousands of millimeters of mercury in the example, which is similar to the example that we have just seen. At these high levels, the amounts of oxidizing free radicals literally swarm the enzyme systems designed to remove them, and now they can have serious destructive and even lethal effects on the cells. One of the principal effects is to oxidize the polyunsaturated fatty acids that are essential components of many of the cell membranes. Another effect is to oxidize some of the cellular enzymes, thus damaging severely the cellular metabolic systems. The nervous tissues are especially susceptible because of their high lipid content. And thus, one of the major parts of oxygen toxicity is due to this oxidizing free radicals. Next, we move on to decompression sickness. Decompression of the diver after excess exposure to high pressure. When a person breathes air under high pressure for a long time, the amount of nitrogen dissolved in the body fluids increases. The reason for this is the following. Blood flowing through the pulmonary capillaries becomes saturated with nitrogen to the same high pressure as that in the alveolar breathing mixture. Over several more hours, enough nitrogen is carried to all the tissues of the body to raise their PN2, that is the partial pressure of nitrogen, also to equal to the PN2 in the breathing air. Because nitrogen is not metabolized by the body, it remains dissolved in all the body tissues until the nitrogen pressure in the lungs is decreased back to some lower level, at which time the nitrogen can be removed by reverse respiratory process, that is just by expiration. However, this removal often takes hours to occur and the source of multiple problems collectively called decompression sickness. The first problem is the volume of nitrogen dissolved in the body fluids at different depths. At sea level, almost exactly 1 liter of nitrogen is dissolved in the entire body. Slightly less than one half of this dissolved nitrogen is in the water, and a little more than one half in the fat of the body. This is true because nitrogen is 5 times as soluble in fat as in water. After the diver has become saturated with nitrogen, the sea level volume of nitrogen dissolved in the body at different depths is as follows. Several hours are required for the gas pressure of the nitrogen in all the body tissues to come nearly to equilibrium with the gas pressure of nitrogen in the alveoli. The reason for this is that blood does not flow rapidly enough and nitrogen does not diffuse rapidly enough to cause instantaneous equilibrium. The nitrogen dissolved in the water of the body comes to almost complete equilibrium in less than an hour, but the fat tissue requires 5 times as much transport of nitrogen and having relatively poor blood supply reaches equilibrium only after several hours. For this reason, if a person remains at deep levels for only a few minutes, not much nitrogen is dissolved in the body fluids and tissues. Whereas if the person remains at deep level for several hours, both the body water and body fat become saturated with nitrogen. And thus we move on to decompression sickness, which have several synonyms, which include bends, compressed air sickness, Caisson's disease, diver's paralysis, and diverism. If a diver has been beneath the sea long enough that large amounts of nitrogen have dissolved in his or her body, and the diver then suddenly comes back to the surface of the sea, significant quantities of nitrogen bubbles can develop in the body fluids, either intracellularly or extracellularly, and cause minor or serious damage in almost all areas of the body. Depending on the number and size of the bubbles formed, this is called decompression sickness. The principle underlying the bubble formation are shown in the following figure. In the figure, the diverse tissues have become equilibrated to a high dissolved nitrogen pressure of PN2 of around 3980 millimeters of mercury, about 6.5 times the normal amount of nitrogen in tissues. As long as the diver remains deep beneath the sea, the pressure against outside of his body or inside, which is 5000 millimeters of mercury, compresses all the body tissues sufficiently to keep the excess nitrogen dissolved. But when the diver suddenly rises to sea level, the pressure on the outside of the body becomes only 1 atmosphere, which is 760 millimeters of mercury. While the gas pressure inside the body fluid is the sum of the pressures of water vapor, carbon dioxide, oxygen, and nitrogen, or a total of 4065 millimeters of mercury, 97% of this is caused by nitrogen. Obviously, this total value of 4065 millimeters of mercury is far greater than the 760 millimeters of mercury pressure on the outside of the body. Therefore, the gases can escape from the dissolved state and form actual bubbles composed almost entirely of nitrogen, both in tissues in the blood where they plug many small blood vessels. The bubbles may not appear for many minutes to hours because sometimes the gases can remain dissolved in a supersaturated state for hours before bubbling. And these bubbles, by blocking small blood vessels, can cause serious damage and even be fatal to the diver. The symptoms of decompression sickness of bends. The symptoms of decompression sickness are caused by gas bubbles blocking many blood vessels in the different tissues. At first, only the smallest vessels are blocked by minute bubbles, but as the bubbles coalesce, progressively larger vessels are affected. Tissue ischemia and sometimes tissue death are the result. In most people with decompression sickness, the symptoms are pain in the joints and muscles of the legs and arms, affecting 85 to 90% of the persons who develop decompression sickness. The joint pain accounts for the term bends that is often applied to this condition. This was all we had for today. In this particular lecture, we have gone through the various aspects of aviation, space, and deep sea diving physiology. The references for these slides are the chapter 43 and 44 of the textbook of medical physiology by Arthur C. Guyton, the 11th edition. I thank you for listening to this video.